In section 410, we're going to be talking about antiderivatives. So basically what that means is we're going to be working backwards. So if I give you a derivative, I want to know what is the original function. We're going to call that the antiderivative. So example 1 says, find a function whose derivative is f of x equals 2x. Hopefully we've taken derivatives for long enough that we just know, just by guessing in our heads, what function gives us a derivative of 2x. Well, the answer would be y equals x squared. It could also be y equals x squared minus 4, y equals x squared plus 5. There's actually an infinite number of possibilities here. And so what we're going to do to write the general antiderivative, to describe the fact that we could add any constant to our function and it would still have the same derivative, is we're going to tack on a plus c at the end of our answer. All right, so again, y equals x squared, y equals x squared minus 4, etc., are all antiderivatives. The general antiderivative would be y equals x squared plus c, where c can represent any constant. And so from now on, when we find antiderivatives, we're just going to always tack on that plus c. So let's try a couple more, and then I'll give you some formulas or rules for antiderivatives. So again, we're working backwards. We're trying to figure out what function would give us a derivative of sine of x. What about e to the x? Or negative 1 over x squared? Well, the first one, it would be negative cosine x, and then I have to put on the plus c. That's because I know the derivative of cosine x is actually negative sine x. And so if I want to get a positive sine x, my original function or my antiderivative would have to be negative cosine x. All right, what about the e to the x? What function has a derivative that is e to the x? Well, the answer is e to the x. And then I put on that plus c to indicate that we could add any constant, and it's still an antiderivative. I don't know if anyone knows the last one, negative 1 over x squared. That's the derivative of 1 over x. When you take the derivative of 1 over x, you get negative 1 over x squared, and then of course plus c. Now, some of you might not have recognized that last one, and I don't expect you to recognize every single derivative, and so therefore, I think we need to come up with some properties and rules for antiderivatives. Before I do that, though, I'm going to give you some notation and vocabulary that I'm going to be using. I've been using the word antiderivative. We can also call this the indefinite integral. Those two words are interchangeable. They mean the exact same thing. Symbolically, we are going to write antiderivatives, or indefinite integrals, using this integral symbol, the function that we want to integrate, and then we're going to put a little dx there, which is really just part of the notation, but it tells me what the variable is. So for example, in example 1, we said the antiderivative of 2x is x squared plus c. And so in orange, I have written out how we would write that in symbolic form. So the antiderivative of 2x, so this thing right here, the 2x, you're trying to figure out what function has a derivative that equals 2x. And there's my answer, x squared plus c. All right, so this is the notation I'm going to be using for antiderivatives. And I just have written out in words some things that I've said already. So I just wrote out basically as a sentence, hopefully what I just said out loud, y equals x squared plus c is the antiderivative of y equals 2x. This is equivalent to saying y equals 2x is the derivative of y equals x squared plus c. So antiderivative, we're all of a sudden doing the opposite or the inverse of finding derivatives. All right, so now let's get our big list of antiderivative, or we could call these integration formulas. All right, so my first 4 formulas I have written out. First one is saying if we want to integrate or find the antiderivative of a constant, we'll get kx plus c. So here's an example of that. The antiderivative of 5 would be 5x plus c. And that's because when you find the derivative of a linear term, like 5x, the slope is just that number 5. And so when you're working backwards, if you want to find the antiderivative of a constant, you just tack on an x. All right, so there's my first property. Second property says if you want to find the antiderivative of a sum or a difference, you can do each piece separately. So for example, if I want to integrate or find the antiderivative of 3 plus 2x, I can do each piece separately. We just learned that when you have a constant, like 3, you just tack on an x, you get 3x. And earlier in example 1, we saw that the antiderivative of 2x was x squared. You don't have to tack on the plus c twice, you only just put it on one time at the end. So 3x plus x squared plus c. The great thing about antiderivatives is you can always check your answer by finding the derivative and making sure you get what you started with. All right, so that's my second property. Let's take a look at this one that I have circled, x to the n. So this is an important formula. This is our power rule for antiderivatives. If you want to find the antiderivative of x to the n, you get x to the n plus 1 divided by n plus 1. This really is my derivative rule backwards. So remember, when we find derivatives, we end up multiplying. We bring the exponent down, so we're multiplying. And then we subtract 1 from the exponent. Here we're going to do the opposite. We have to add 1 to the exponent, and we have to divide. So I have written down 2 examples just to illustrate what that formula is telling us with numbers. The antiderivative of x to the third would then be x to the fourth over 4, always plus c. The antiderivative of x to the seventh would be x to the eighth over 8 plus c. And so I added 1 to the exponent and then divided. And so that's our power rule for antiderivatives if we want to work backwards. All right, finally, this property antiderivative of k f of x dx is saying if you have a constant times a function, you can actually pull that constant out front. So for example, if I had 3x to the fifth, the 3 is actually going to stay there, or you can pull it out front, and then just use the formula we learned on the x to the fifth. So the 3 stays there. For the x to the fifth, you get an x to the 6 over 6, and then plus c. Now I would reduce that. The 3 over 6 is the same as a half. But that shows kind of the basic idea of, I guess, the second property. All right, and so then I just filled in the rest of these. The rest of these are really all of our derivative formulas written backwards. So this is telling us the antiderivative of cosine x is sine x. That's because the derivative of sine x is cosine x. And so hopefully some of these look familiar. For example, you integrate secant squared, you get tangent, because we know secant squared is the derivative of tangent. This might be a good time to pause the video and make sure you have all of these formulas written down in your notes. When you move on to Calc 2, it's going to be expected that you have all of these ones memorized. So good thing to get down in your notes. All right, so let's just do some practice. Let's practice using these formulas to find antiderivatives. So let's find the following. We are going to find the antiderivative of 4 divided by x to the third. Let's do that one first. So I really want to use the power rule, that x to the n rule. And so I'm going to bring the x to the third to the top and write it as an x to the negative 3. Now I can use my power rule, and that constant, the 4, stays there. This is a lot like when you were taking derivatives. If you had a constant times a function, the constant just stays there. So the 4 stays there, and then I add 1 to the exponent. I get x to the negative 2 divided by negative 2. And I always have to put a plus c on at the end. I do want you to take this answer a little bit further. I'd like you to rewrite it using a positive exponent and also reduce. We do have a 4 divided by negative 2. 4 divided by negative 2 is negative 2. And then we can take that x to the negative 2, bring it to the bottom. We get negative 2 over x squared plus c. All right, my second example, 2 plus 1 over x. Let's see, this one we potentially don't have to show a lot of work for because we have formulas. The 2 turns into a 2x, and the 1 over x becomes a natural log of the absolute value of x. That was one of our formulas on the previous slide. Now, 1 over x is the one case where that power rule doesn't work. You could write that as x to the negative 1. But if you add 1 to that exponent, you get x to the 0 divided by 0, which is undefined. So that power rule doesn't work when you have a 1 over x. Works for every other power of x. So when you have a 1 over x, you just have to remember, oh, that's the derivative of natural log. So I'm going to get natural log absolute value of x. Okay, and yes, I always put that plus c on there. All right, here's 2 more. If I want to integrate 3x minus sine x, I do it one piece at a time. The 3 stays there. That's an x to the 1, so it becomes an x squared over 2. The antiderivative of sine x is negative cosine x. So I guess negative cosine x turns into a plus cosine x. And there's my final answer. Again, I made sure to add that plus c at the end. Now for my fourth example, unfortunately there is no quotient rule for antiderivatives. There's no product rule for antiderivatives either. And there isn't even a direct chain rule. We'll learn there's some ways to kind of undo the chain rule, but there isn't a straightforward product rule, quotient rule, chain rule for antiderivatives. And so because this is a quotient, we actually have to simplify it. We have to do the division before we can find the antiderivative. All right, so that's what I just said. No quotient rule for antiderivatives. And so how I did this problem is I decided to write that cube root of x as an x to the 1/3, and then I moved it to the top, so it became an x to the negative 1/3. Now I can distribute, and when we multiply, we add the exponents. So 2x to the 1 times x to the negative 1/3. 1 minus 2/3 would be 1/3. And then we have a minus x to the negative 1/3. Now I can use my power rule. First term, the 2 stays there. We add 1 to the exponent. 2/3 plus 1 is 5/3. Divide by 5/3. And then for the other term, add 1 to the exponent. Negative 1/3 plus 1 is 2/3. Divide by 2/3 plus c. Again, I don't want you to leave your answer like this. I don't want any complex fractions in your answer. So we're going to copy dot flip. Dividing by a fraction is the same as multiplying by its reciprocal. So that divide by 5/3 turned into a multiply by 3/5. So there's my multiply by 3/5. And then I did multiply straight across, and that's how I got the 6/5. And then the divide by 2/3 turns into a multiply by 3/2. All right, and so there I have circled my final answer to this problem. All right, so moving on, one application of antiderivatives is we can use this concept to solve some simple differential equations. All right, it's a lot of words. So what I have written on the screen is an example of a differential equation. A differential equation is basically just an equation that has a derivative in it. The dy dx is the derivative. And if we're trying to find a solution to a differential equation, we're basically trying to find the function. What is the function y equals that satisfies this equation? In other words, find the general solution of dy dx equals 5x is basically asking us, find all antiderivatives of 5x. That's what this problem is asking us to do. So it's exactly what we've already learned. It's just written using different words, slightly different vocabulary. Okay, find the general solution of y prime equals 5x. So that means I have to find the antiderivative of 5x. 5 stays there. We get an x squared over 2, and then plus c. So y equals 5x squared over 2 plus c would be my general solution. Now example 5 is really similar, except it says find a particular solution. And then they give us more information. So we've got the same differential equation, dy dx equals 5x. Now we want to find a particular solution given that y of 2 equals 4. All right, so particular solution means we're going to find one specific antiderivative, or in other words, we're actually going to figure out what that constant plus c is. So we just have one extra step to do in this problem. We're still trying to find the antiderivatives, but we're going to go further and figure out what is the plus c. Okay, so I started this problem the exact same way as the previous one. The antiderivative of 5x is 5x squared over 2 plus c. Now I'm going to use the fact that y of 2 equals 4 to find that constant. So I took the 2, I plugged that in for x, and then I took the 4 and I plugged that in for y, and then I can actually solve for c, figure out what c is. So in this case, I get 4 equals 10 plus c, so that means c is negative 6. And there's my final answer in purple. My specific antiderivative, or my particular solution, is 5x squared over 2 minus 6. All right, let's look at another one that's similar. So same process, just different equation. Solve f prime of x equals 4 secant squared x, given that f of 0 equals 3. So because they're giving us an initial condition, because they gave us that point f of 0 equals 3, that means they're asking for a particular solution here. So I'm going to start by finding the antiderivative of 4 secant squared x. The 4 stays there. This one you just have to memorize. It's on that slide from earlier today. But we're really trying to think, well, what function has a derivative that's secant squared? And the answer is tangent. So my function would be 4 tangent x plus c. And then because we're trying to find a particular solution, I'm going to take that information given. I'm going to put 0 in for x, 3 in for y, or f of x, and then figure out what the c is. Tangent of 0 is 0, so I end up getting c equals 3, and that makes my final answer f of x equals 4 tangent x plus 3. All right, this one is similar, but it's a little bit different because I'm giving you a second derivative. The goal is still to find the original function, f of x. But now we're told f double prime equals 3x, and we're given two pieces of information. F prime of 1 equals negative 3, and f of 1 equals 2. So if they give us information about the second derivative, and we want to find the original function, what do you think is going to happen? What are we going to have to do here? We're going to have to take the antiderivative twice. So if we find the antiderivative of 3x, that's just going to give me the first derivative. So if f double prime is 3x, then f prime is the antiderivative of 3x. So I guess that would be 3x squared over 2 plus c. And then notice they gave us enough information to find that plus c. We were told that f prime of 1 is negative 3. So we can put 1 in for x and negative 3 in for the f prime. And then we can do some math, figure out what c is. I ended up getting c equals negative 9 halves. I just did minus 3 halves. Should be minus 4.5 or minus 9 halves. So f prime of x is 3x squared over 2 minus 9 halves. So when we take the antiderivative of our second derivative, that gives us our first derivative. And so if we actually want to find the original function, we're just going to have to repeat this process. So f of x is going to be the antiderivative of 3x squared over 2 minus 9 over 2. The 3 halves stays there. The x squared became an x to the third over 3. Minus 9 halves is a constant. So that becomes minus 9 halves x, and then plus c. They told us f of 1 equals 2. We're going to use that to figure out what the c is. So I took 1, I plugged that in for x. I took 2, plugged that in for f of x. I did also, if you look at my function down here, I canceled those 3's out, and that's how I got this 1/2. So I actually said my function was 1/2 x to the third minus 9 halves times x plus c. Put 1 in for x, 2 in for y. I ended up getting c equals 6. And so there's my final answer circled at the bottom. 1/2 x to the third minus 9 halves x plus c. Finally, let's take a look at an application problem that goes through the same process. So we learned in the past that velocity is the derivative of position. So that means position, which I'm calling s, is the antiderivative of velocity. And we learned that acceleration is the derivative of velocity. So therefore, velocity must be the antiderivative of acceleration. So let's see if we can use this information to solve the following problem. It says a car traveling 50 miles per hour. You know, let's make those units the same. I don't want to have to do a unit conversion. So let's say the car is traveling 50 feet per second. It brakes with a constant deceleration, so it's slowing down, 40 feet per second squared. Okay, so the information that they're giving me, the car is traveling 50 feet per second. That's its initial velocity. That would be its velocity before it starts braking. So I'm going to call that v of 0. The velocity at time 0 is 50. The acceleration of this car is going to be negative because it's braking or slowing down. So negative 40 is my acceleration function. So if I want to find the velocity function, I'm going to have to integrate my acceleration. So velocity should be the antiderivative of negative 40. And this time, notice I put a dt there because the variable was a t. That's just how that notation works. That little dx dt really tells you what the variable is. So negative 40 is a constant. So its antiderivative would be negative 40t, and then of course plus c. We can figure out what that constant is using the fact that when t is 0, v, or the velocity, is 50. So I plugged in 0 for t and 50 for v, and I ended up getting that constant c is 50. So my velocity equation is negative 40t plus 50. It's basically describing a car that's going 50 feet per second, slowing down by 40 feet per second. Okay, part B says, how far will the car travel before stopping? How far will the car travel before stopping? So it's asking us for a distance or a position. So we're probably going to need to find the position function. And then it says something about stopping, so we better figure out when does the car stop moving. So two things we're going to have to do here. All right, in other words, this is what I tried to say in a little bit more compact form. This problem is asking us to find the position, s of t, at the time that v of t, or velocity, equals 0. So the first thing I'm going to do is figure out, well, when does the car stop? When is velocity equal to 0? So I just set 0 equal to my velocity, and then I solve for t. I ended up getting t equals 1.25 seconds. So the car will stop after 1.25 seconds. So we want to find the position of the car after 1.25 seconds. So the next thing I have to do is find my position function. Position will be the antiderivative of velocity. So I'm going to take the negative 40t plus 50 and integrate that. I get negative 40t squared over 2 plus 50t plus c. And I might as well reduce that to a negative 20t squared plus 50t plus c. Now, it turns out, since we care about how far did the car move relative to its starting position, that plus c doesn't really matter in this problem. I think the easiest way to think about it is just assume that the car started at 0 and just let that constant equal 0. Because we're really trying to find a change in position. How far did it move? So I'm just going to let that constant equal 0. And then we want to find how far did it travel, its position after 1.25 seconds. So I took that 1.25, plugged it in for t, put all of that into my calculator, and got a little over 31 feet, 31.25 feet actually.